right, I think it's time to start. What we are going to do today is to, let me see. All right, that's clear there. Okay, we are going to start solving some problems on capacitance, but we're going to do two things at the same time. One will be to do capacitance in a, calculate capacitance in a cylindrical system. And then, so we're going to start with a charge in a cylindrical system, all right? Then we are going to go to a two-conductor cylindrical system, which we call it coaxial conductor, all right? That's the most useful thing. I don't know whether I can show you a coaxial here, maybe this one. These cables here, it's not TV, but this cable, the thicker one here, is a coaxial cable. And they have, this one probably not. It's not very easy. No, these ones are not coaxial. Usually it's for TV. Usually coaxial cables are much thicker than the other ones. This is thick because it has a much thicker conductor. But they are like this, if not thicker, like this thick cable here is not thicker, but at the end, they have a connector that is, it looks like what I have on the board. It's a round thing, and then inside you can see that there is another conductor that comes out, like a pin, comes out like a pin. And then when you connect it, you have to connect it well so it goes, the inner conductor goes to inside the TV set, connects with the inner conductor, the outer connects with the outer conductor. The outer conductor outside is grounded, right? So this is the coaxial, and the parallel plate are the most useful because they will be, as you will see, I will show you towards the end of electrostatics, which is going to be sometime next week. I will show you how you go from parallel plate to microstrip, what people are using primarily in printed circuit design, and coaxial, which is for higher frequencies. And there are different variations. People are using it for high frequency applications. Usually ground stations, when you have the repeaters on ground stations, usually they will use coaxial cables. Printed like parallel plate, what we call parallel plate waveguides or parallel plate lines or microstrip or strip line, all kinds of different names, depending on slight variations in the geometry. These are good for integrated circuits. But when it comes to large like systems, if for example, you have a military radar that is sitting on top of a Humvee, or you have another naval radar, which is on the top of the bridge of a ship, or you have a repeater, which is on tower, all right? Of course, you have to move, you connect your top antenna to whatever equipment you have down there, and then you need a cable. And these cables are coaxial. So, very useful. Let me start with a simpler problem here. So the problem is, I will solve it for you here, and the solution is also included, but as you will see me solving it, I think it's gonna be easier as opposed to just showing you these numbers. Okay, so we'll add a page. I think solving is better. Do you know why it is, why we learn better by watching somebody else solving the problem, as opposed to watching a PowerPoint? Because the brain can memorize time frames, like one coming after the other. And there is a way on the basis of memorizing those time frames to have an anticipatory kind of intelligence. So you see one thing and then your brain anticipates the other. And that's how the brain learns. So it's very interesting. A lot of our faculty have, we went through a phase when we were printing everything on a slide, and then we would show it and the student says, well, not good somehow. And now I don't create slides because it's so much time for too little. But some of my husband, for example, is a faculty member. He creates slides, but now he writes on the slides too. Anyway, double the work. But this one, so here is the problem. We have a cylinder. Well, that's not a good cylinder. Let me erase it. Okay. Okay, I wonder why. All right, this is a better one. And this cylinder, it's infinite long for the moment, but we consider, of course, a finite section of it to be able to do the problem, to be able to do the calculations. And a lot of times, if they're infinite long, my advice to you will be to first of all, draw them both in 3D, so you have the visual, and then do the cross-section as well, all right? Because the 3D gives you a sense of what is happening in 3D, I mean, in the visual, our visual space, and is important. The 2D, which is the cross-section here, gives us more detail, all right? So this is along, since this is a cylindrical coordinate system, is going to be along the z direction. Now, in this particular problem, what I do is to tell you that I have this charge. I have a charge which is distributed that I gave the problem for a meter, as a matter of fact. So some time ago, I don't remember when, but there is a charge here, not at the center, which I could put a charge at the center. I did not do that. In this particular case, there is a positive charge, but distributes on a cylindrical surface, all right, in here. And this surface, in fact, I will make it like this. So this charge here distributes along the surface. All right, I will put only a few there. And then I do this. So what I'm asking then to do, okay, the other ones, is to find the electric field here inside the cylinder. This one is a conductor. All right, and for the moment, we are only looking inside the conductor. We have not decided what we're gonna do with the outside, all right? That is gonna come next in the problem. Okay, it's a perfect conductor, so this outside. So it's a perfect cylinder that has this charge, all right? And in fact, in 3D, it's gonna show like this here. All right, the charge distributes inside the conductor, but on a surface that is, how could I say, it's very thin, the charge is there, there is nothing material inside the conductor, only the charge, think of this distributed this way. And then I would like you to find the field, we'll find it together inside. How many regions do you see? We don't care about the outside for a moment. How many regions of interest do you see in this problem? 1, 2, 3, 4, how many? Yes, for this one. 2. One is, and I will shade them slightly so you can. One is here inside, all right? Because that is a boundary that is created by the charge. It's not a physical boundary, but wherever you have boundaries, either created by charges, so by sources or by materials, you always have to divide your space according to those boundaries. So here we have one here inside, and 2 outside. We have these 2. Okay. How are we going to solve a problem like this? You remember this problem, 3D here, has what? This problem has an perfect cylindrical symmetry. All right, this is along phi practically, and along z is constant. All right, so at any point on z, you see the same thing. Every point along the phi direction of the cylinder, you see the same thing. All right, if you are at constant rho, you see the same thing no matter where you are. So that is a cylindrical symmetry, which means that I will apply which law to find the electric field? We have 2 possibilities. Gauss's law, right? We have 2 possibilities for the electric field. We have Coulomb's law and Gauss's law. These are the 2 we have learned, all right? And we said they're connected. It's not like you use one and then somehow you have a problem with the other. No, you can go from Gauss's law and prove that there is Coulomb's law. But the starting point is the critical one, all right? So we start with Gauss's law because of the symmetry. If somehow we did not have symmetry in this problem, all right, it was a finite cylinder with 2 ends and inside there was no symmetry, then you could not use Gauss's law. Then in that case, you would have to go through Coulomb's law, which in fact is a more complicated one. All right, so Gauss's law. What do I do with Gauss's law? I look at its section separately. So I'm going inside, all right? I'm going inside, and then what do? I just create what I call a Gaussian surface. What is a Gaussian surface? I just follow the boundary that I have defined, which now carries the charge, all right? So a Gaussian surface inside is gonna look like this. It's another cylinder, okay? It's a Gaussian surface, it's another cylinder. So why do I have to create this surface? Because Gauss's law says the following, that the divergence of D equals rho, or Q, if you want to call it Q in this case. Let me call it Q. Rho is the density, all right? So in this case is Q. It is distributed over a surface, practically. So because it is distributed over a surface, and this surface is infinite, is an infinite problem, what kind of density will characterize this charge? If I had given you the total charge here, Q is total. Had I given you the total charge, how would you find this one here? What kind of charge density is that? I can show it like this also. All right. What kind of charge density is this? In 3D, it would have been what? Because it's surface. No, it's a surface. The charge distributes on a surface. So it will be surface charge, all right? That is the line, exactly. So surface charge in the 3D. If I were to go to the 3D problem, like up here, you see all of the charges with the positive signs here, that distribution would have been a surface charge. However, because when I'm going to cross sections, I really already have dismissed the z direction. And why have I dismissed the z direction? Like I go automatically from a 3D problem to a 2D one, which is the cross section, because z does not exist in any solution. If it's infinite long, wherever I go along the z-axis, I will see the same solution. Otherwise, it would have been finite, all right? Obviously. But for infinite long, it means that anywhere on the z I see the same, which means whatever solution I find is not going to have a z in there, all right? So now I go immediately from a 3D problem to a 2D problem here, okay? And what do I see here? That the charge is a line charge. This Q total that I will give you is not gonna be only in coulombs. The Q total is gonna be a charge, therefore, in coulombs per length, all right? Because obviously is the charge only of the cross section. And if I had a finite section of this, I cut a section out of this infinite cylinder, that's where the charge is total in coulombs. But now, because I have an infinite long problem, I cut a cross section, the charge is not gonna be just coulombs, all right? It's gonna be coulombs per meter, which means that I call this a line charge, but what the units will be for this line charge? It will be coulombs per meter squared. So I'm not going wrong with the initial problem, all right? Initially, this is a true problem. The 3D is true. The 2D is a mathematical simplification. In 3D, the total charge is coulombs, all right? And every other, this one, as I said in 3D, the pluses here that you see will be a surface charge, which means that that surface charge would have to be in coulombs per meter squared. That's physically, that's what happens in real life. However, now we simplify the problem mathematically and we go to 2D, all right? Like here, we simplified mathematically, we go to 2D. But that does not mean that our units will also alter, because units there and coulombs is a physical entity. A mathematical change, alteration, if you like, in the problem, modification in the problem, should not change the units, all right? Should not interfere with the physics. So the units here, even if I call it a line charge and I will treat it like this, the true units will be in coulombs per meter squared. Do you understand that part? Okay. Now, so now we go back to the cross-section, two-dimensional problem. All right, so the cross-section here is a 2D. This is 3D. And we went from one to another because of cylindrical symmetry. So you remember, it was not arbitrary. We never do arbitrary things in engineering, as you know. Okay, so that is supposed to be QL. On this 2D problem, Gauss's law in 2D tells us this. Now, this is a 2D problem in cylindrical coordinates, which we will need to keep in mind. All right. So, if you go to if I don't have to do it immediately, but I will do that. So we go to region 1. Region 1. In region 1, we are applying Gauss's law on this green line surface that I have showed you. All right, or line. I mean, I meant to say cylindrical, but eventually it's a line for us. Okay, so here when we apply Gauss's law in 2D, the 3D volume, the volume integral becomes a surface integral, all right? Everything goes down by one dimension. So to write it here, we know that in 3D, we have that the divergence of D, volume integral, dV, will be equal to the surface integral, all right, of D dot ds. All right. Now, in 3D, the surface has a direction, all right, obviously, and the surface retains its direction here. Even if I cut it, what is the direction of the surface of the cross-section? Look at the 3D. What is the direction of this surface, which is the cross-section? The outside surface on the 3D has this direction. Okay? This cross-section, what direction does it have? What do you think? The cross-section. What direction did you say? No, the R direction is the direction of the surrounding surface. All right, of the one, this is a cross-section here, the purple. The surrounding surface is this one. All right, that has the R direction, because in cylindrical coordinate systems, R is this one. R is, let's say this is your point, all right? R is this one. A sub R, all right, that direction. A sub Z is this. And what is A sub phi? If I draw the X coordinate here, A sub phi is gonna be this one. It's gonna be practically, if I am at this point, it's gonna be parallel to the circle, the cross section at that point. That's the phi direction. All right, this is 3D. If I take this down to 2D, this is the R direction. All right, this is the phi direction. But the Z direction does not exist because I've eliminated by considering only a 2D problem. And therefore, for the cross section, the direction of the surface is the AZ. All right, the cross section is the purple one. Its direction is this, which is the Z direction. All right, so you need to remember that the cross section always of a cylindrical system has a direction along Z. Every surface has a direction, as we said. All right, every surface. There is no surface with this direction unless you know what the direction is and you eliminate it just to make your things easier. However, every surface has a direction, and even our surface here has a direction in the cross section. So if I go now from 3D to 2D, if I go to 2D, I just keep one direction. So the volume integral is going to become this surface integral, okay, of this. However, instead, because surface has a direction, I'm going to practically take the inner product of this with the direction that I have eliminated. All right. So yes, I recognize that has a direction, but I have, because I eliminate the Z direction, I just therefore do this to be able to eliminate and be able to have a, instead of dV, I will have a ds, but without a direction. So practically this one gives me ds. Okay, and then instead of a closed surface integral here, which was for the 3D problem, I will have a line integral. All right, and lines do have a direction, and that's going to be a closed line integral of d, which is not a function of z, but all of the other, the r and phi, dl. And what is the dl direction? What used to be the surface, which was the outside, all right? But the outside surface has now been reduced into a line. So C here, C, the directions, the line, I called it C, is going to be, I'll give it a different color so now you can identify it. It's going to be this one. Okay, now, what did I say? I say that this surface here, which I call C, line here, which I call C, has a direction. In fact, yes, I saw that. It's a closed, first of all, integral, and has a direction. I put it here. What is the direction? How do we define the direction? From the right-hand rule. If the Z, if the direction of the surface is the Z, that's important. That's why it is important to remember that our surface has a direction. If the surface, and that we're going to use it a lot in magnetostatics, all right? If the direction of the surface is Z, the direction of the line that encloses the surface is found like this, all right? Therefore, always to keep it in mind, if a surface has a direction like this is a surface, has a direction, the line that encloses the surface is a closed line, first of all. You cannot enclose a surface without coming, without having the beginning and the end of a line to meet. All right, understandable. The direction then of this line that encloses the surface is this. What if the surface had the opposite direction? What would have been the direction of the line that encloses the surface? The other way. Yes. Okay. Every surface has a direction. What I mean? Okay, the board is a surface, all right? And the surface always is part of a surface that encloses a volume. So the wall, you may argue that we are the volume, and these walls, all of these here, are the surfaces that enclose us. If we are the volume, those surfaces have a direction that goes from inside here outwards. That's the definition. All right, the surface that encloses a volume always has a direction outwards from the volume. If this surface is defined as the one that encloses, if there was here, this is another classroom, I think. If this surface is defined as the one encloses the other classroom, then the direction, and therefore the volume that surface encloses is on the other side, then the direction for that surface is this way. So surfaces always have direction. And why is that important to remember? Because the surface can be like this, all right? And the surface can be like this. If two surfaces are like that and are identical, they don't have the same direction. So you have to show like a vector. If there's a vector like this and there's a vector like that, you can say I have two vectors, their magnitude is 2. Is that enough? No. You have to know how the vectors go, even if they are on the same plane. Not forget about the 3D. We're talking even about the same plane. If I have two surfaces, like I have a bigger surface now, assume that this is a surface, all right? The inside, that's a cylindrical surface. It's like ours, like a coaxial, as a matter of fact. That's how coaxial look. And this is the dielectric, the gray. Okay, if this is a surface, there are practically, if that were to be hollow, all right, there are 4 surfaces that surround this material. The inside surface, this one and that one, all right? Well, yes, there are more than 4. In the inside surface, no, 4. This one and that one, 3, and the outside surface, 4. Now, these two surfaces are identical. However, because they are part of a surface that surrounds the same volume, they don't have the same direction. This surface has a direction this way, and this surface has a direction that way. The inner surface has a direction inside. The outer surface has a direction outside. That's how we define surfaces, because that's the best way to define a surface. All right, with their area and the direction. And there are some surfaces that have multiple directions, like for example, don't see this cylindrical system where the direction of these surfaces are, and the direction of this surface is minus a sub r. This is positive a sub r, this is minus a sub r, it looks inward, inside. This is a sub z, for example, this is minus a sub z. One of the two is plus, the other is minus. If we have the system like that, this is plus, this is minus. Now, there are other surfaces that look like this. This one, curved everywhere. If you take this surface, it has elements of it, because it's rippled, that have different directions. If you want to characterize this, even for a graphics problem, let's assume you want to go in AutoCAD and you want to design this purse. How are you going to design it? I mean, you want to design it so you see the ripples to see how the forces here distribute. All right. This is an engineering problem. If you want to make it out of a good material, not like that, and if you don't want to not have ripples, then you have to design it. So you put some weight here, and then the strength of the material keeps it straight and so forth. However, in this surface here, to take it into AutoCAD, you will have to define it into smaller squares, even identical squares, tiny, and then in every square, you have to give it a direction. If you do that, AutoCAD is going to create you this surface. Without the directions, AutoCAD will not be able to create that surface for you. All right, so mathematically and physically, direction is important for surfaces. I'm sorry for the very large explanation, but that's why we use it. Okay, so now we have defined the surface. We have transferred the direction from the surface to the line that encloses the surface. And we have now this integral here. Now, inside in C, do we have on this surface, this is the green surface here, do we have on this surface any charges? No, the charges are outside. We've selected this surface, so they don't. So that means what? It means that this here is going to give 0. All right? And not charge. Okay, let's see what is the other one. So C is the perimeter, if you like, of this green circle. I selected like a circle. And therefore, DL is going to be, so D is going to be constant because we said it's a cylindrical, all right, symmetric. So on this circle, the green one, D is not going to change because we said this is a purely symmetric, cylindrically symmetric problem. So it's independent of phi. R is going to be a variable, but for a given R, like the circle, the green circle, D is going to be constant on this given R. So D here is going to be have only this component and is going to be constant. So practically I move it out of line integral. And therefore, and it's going to be whatever the radius is, all right, at that point. Let's consider that to be radius 1, since it's 1. And therefore, C becomes from 0 to 2 pi, or let me keep it C because it's easier. Don't have to. You can do it either way, but let's keep it that as C dl. All right. And dl is this. Now, C has a direction, and practically what this integral C dl shows us is that we have to integrate around this circle. How much is that? 2 pi? Yes. It's like the perimeter. All right, so that is going to give us, and practically, well, let me see, that is going to give us 2 pi r1, and then you're going to have dr, and that's going to be 0. Okay, so from here, what do we find? That this bar is going to be 0 everywhere inside the circle that carries the charge distribution. Does that remind you of something? Yes. If we are, what it should remind you is the following: that if we are inside the charge, all right, and the charge is like uniform like this, then the electric field is 0 because all of the contributions from each charge will be canceled out by the contributions of a charge which is diametrically opposite. And we've seen that, all right? So inside this hollow, if you like, cylinder, there is no electric field, is 0. Okay, so with that, we came right, let me see. Here we said, I said it somewhere. Outside. I think I asked them for this field outside. Okay, I said 0. So 1 for 1 that says the result is 0. In this meter, since we had done this, I did not ask them to derive it. All right, so I can give you a midterm, for example, for something that we have already derived, and I may ask you to tell me what the solution is. That does not mean that I want you to copy the derivation if we have it in the notes. I just want you to tell me what it is. In this particular case, we had done this problem, and I just asked them, and then their answer, the correct answer would have been that inside the charge in area, for example, 1, the field is 0. And that would have been perfect, all right? For anything that we have done in class, we have solved as a problem in the homework, or we have done as an exercise in class, all of this for here. If I ask you anything like that, don't re-derive it. Just tell me the answer, all right? And if I were to ask you, tell me what it is and why, the only answer that I wanted to hear is, it's 0 because all of the charges cancel each other. They are symmetric, obviously. That would not happen for a non-symmetric case. All right, just because they are symmetric, for every charge, there is another one that cancels it out. And then all of them together. All right. Now, they asked for intensity between, and then we want the intensity between, in region 2, which is between the charge and the metal. All right, and in this case, we will have to just take, we erase all right, so what we're gonna do in this case, I will keep that. So take this and copy it. And then add the page and copy it here, paste. All right. So now I erase this. And what I do, I find a similar Gaussian surface, as we call it, but now that includes the charge. So the green line that I used is gonna go here. All right, that's my Gaussian surface. And is inside 2. If I do exactly the same thinking as before, this is gonna be C. All right, and this is surface S. If I go exactly as I did before, what I will have, I'm not going to rewrite everything from the beginning because it's the same problem. It's just that the divergence of D is going to be equal to this Q sub L. So I'm going to write this expression here. All right. And in this case, the only difference is there because, let me see. We have that in region 2, divergence of D equals Q sub L, wherever Q sub L exists. And then Q sub L is inside this surface, cylindrical, but circular on the cross section. Okay, so practically this integral here gives us what? Because it's a surface integral, it's gonna give us, I'm gonna replace this by Q sub L, and then it's gonna give us the surface integral of that surface, all right, which is the cross section. And the cross section, if I am at a distance rho from the center, the cross section, what is the area of this green circle? Pi rho square. Is that right? And then also Q sub L on that side. And on the other side, what do I have? I will have dr, all right, and then 2 pi rho. Do you agree with that? How much is dr? Is epsilon not er, because d is equal to epsilon e. Here is free space, is epsilon naught, and therefore we have the dr is epsilon naught er. And from these two, what do we find? That er is going to be 1 over, let me see. It's about, oh, this, excuse me. That's why I got confused here. 2 pi rho. Okay, so it's pi here. And then, sorry, I think, yeah, Q I R. Mistake number 1. The problem that I made here is it is the surface, but QR does not exist on a surface. QR exists only on this line. So practically this is going to be your total Q. Total Q. Let me put it here. Okay, so that is going to be, the integral is going to be total Q as a matter of fact, and not this one. That's my wrong. And therefore from here, this is going to give us that epsilon sub r is, of course, pi remains. Okay, it's going to be 2 pi epsilon naught 1 over rho. Okay, and that's going to be your E sub bar, which in fact, this is what we found here. And it's going to be along what direction? E sub bar, along the direction of D sub bar. All right, and D, you remember what direction D has? D has the rho or R direction. Okay, so this is going to be along the A sub R direction. All right, so it's going to look outwards. So the electric field here is going to be 0 inside. It's like inside there is nothing. Okay, so the electric field, if I were to redo it here, okay, will be the outside, the charges here on this. All right, practically, let's assume that that was not exactly like that. So I will, the charge is like this, positive, on a circle. All right. I will redo them well before I put them on. And then the electric field will look like this. But 0 inside. Why is that important to know? This is a fundamental problem. Why is that? A coaxial, which looks like this, and like this, all right? Two conductors, this one and this one. All right, maybe the inside conductor is also green. There is nothing, it's solid. How the coaxial works, we have a positive charge here. So I want you to think about this problem over the weekend. Here, and because we connect it somewhere, all right? So if this coaxial were to be like this, a finite, all right, and then here, somewhere it would be connected to a voltage source. All right, that's how we have lines. That's what we plug them into the power. We have a source. So from the positive end of the source, all of the charges will go on the inner conductor, but where? On the surface of the inner conductor. Inside the inner conductor is 0 electric field. Remember, no fields inside conductors, perfect conductors. And then what happens to the outside conductor? The outside conductor has all of these electrons. They see these positive charges, and all of the electrons from the outside conductor come to face all of these positive holes, charges. Remember, we were talking about that in the planar. The same thing concept applies to the cylindrical. So what happens to the outside of the external conductor? Yes, all of the positives will try to go here. But we are not going to allow them because we are smarter than this. We don't want these positives to be out because they're going to radiate. Could you believe it? Have a coaxial line to feed your TV and then this line to act as an antenna? That's why TVs sometimes don't work. They have all of this noise, you know. They have double images. They have all kinds of different things, usually noise, because your conductor probably is not well grounded. The first thing I would do is to check that one. So what do? We put a ground here. And when you put a ground, all of these disappear. When all of these disappear, what happens to the field inside? Would you be able to tell me now how the field will look from what we've seen before, just today? How will the field look? Is it not going to go like this? What do you think? Yes or no? Yes, and how much is it gonna be?
Where did the Q go with this equation?
In this one, the Q.
Yes.
This Q here is the 2 pi, whatever distance is this, say rho, whatever, plus is 2 pi rho plus, which is the circumference, times Q sub L. And why is that happening? Because of the surface integral here. Ah, that's what you mean. It should be here. Sorry. Yes, thank you. Yeah, thank you. So how much is this electric field gonna be there for inside the coaxial? If I use exactly Gaussian, the same Gaussian argument. Is it not gonna be the same like before? Yes, yes. Because if we use Gauss's law, it's not gonna change. All right? It's gonna be the same as before. Okay, so you have an electric field. The next time what we're gonna do is take that electric field, integrate it along a line to find the voltage. And then from the Q that we have and the voltage, we're gonna find the capacitance. And therefore we are gonna know the capacitance of a coaxial waveguide, as we call it, or coaxial conductor, or coaxial line, okay? So, all right, so I'll see you on Monday. No quiz, just focus on doing your homeworks. No quiz for Monday. We are gonna start with quizzes when we, probably I'll give you an exercise on Monday for Wednesday. And then quizzes next Friday, okay? All right, thank you.
You said, wouldn't the 2 pi rho cancel out 2 pi?
Yes, if you put this one, it's gonna be a this Q.
Oh, so it just be
Yes.
the density.
Yes.
Okay.
We started to get